Hello all. Today we'll look at the second module of a subject that is dealing with some advanced data structures. So before moving on to the topics, we need to know what are heaps or what's the working of a basic heap. So moving forward, we know that heaps are related to priority queues. So we'll see what is a priority queue along with what is a heap. You must have learned priority queues in your earlier program like BTech while learning the subject data structures. So basically, a priority queue is a collection of zero mode elements, and the specialty is that each element will have some priority or a particular value given to it of according to its importance. So it can be implemented using, it's basically a queue, you can see it by the name itself, and can be implemented using any kind of data structure like array, etc. So unlike the normal queues, which acts as a first in, first out method, you can see the order of deletion is determined by this priority. That is, who is the person or who is the next item that is to be executed or served is determined by that element or item's priority. So based on whatever order they come in, only depending on the priority, they will be removed from the queue. So elements are deleted either in increasing order of priority or decreasing order of priority. It depends on what is your application. Okay. Basically, priority queues will have these sets of operations like finding an element, inserting a new element, deleting an element. Finding an element is basically you're searching for the element in the array or the queue. Now, basically, there are two kinds of priority queues, that is min priority and max priority. So depending on what kind of deletion we require or finding we require, you may have to maybe select the maximum priority or you may have to select the minimum priority. In a minimum priority queue, you can see that it deletes or finds the element with the minimum priority. So you have a queue like this. Suppose if you have an array which consists of maybe two items, and this is the element and this is the priority. Okay, and suppose you insert element say 10 which has a priority 1, then you insert element say 2 which has a priority 4, another element 8 with priority 3, another element 11 with priority 2, etc. So you can see the order in which they will be deleted is normally a priority queue has or a queue has two pointers, that is a front pointer and a rear pointer. So in the rear pointer, so currently the rear pointer will not be here. The rear pointer will be where the last element was entered. So every time we insert an element, we increment the rear pointer. The first time the front and the rear pointer will be beyond this queue, say -1, it will be initialized as -1. When the first element is inserted, both of them will be pointing to the first location. But later on, you can see But later on, as the number of elements increases, the rear pointer will be incremented, and one by one, the last element, whichever was inserted, the rear pointer will be pointing to that location. Okay. Now, whenever you delete element, you use the front pointer. So using the front pointer, we move forward and we delete each element. Suppose I want to delete the first element, I'll be just removing 10 from the array and F++ will be done. So that front pointer moves here. Okay, so we don't do that here. Why? Because this is not the way it is deleted from the priority queue. So let us see when we delete a minimum element or a maximum element from the priority queue, if it has a priority value associated with it, then we look at that. Okay, say for example, if 1 is the priority, so I decide that the number 1 has the highest priority when compared to the number 10. Okay, or you can have a reverse order also. I can decide 10 has the highest priority, then 10 will be the element having the priority value 10 will be the most important one that has to be removed or found. In this case, I'm deciding the least value, that is 1 has the highest priority. So if 1 is the highest priority, then naturally the next priority will go to the element which has a priority 2. Next, it will go to the element which has a priority 3, and so on. So the order it will be removed will be first this, and then this one will be removed, then this one, and then this one. So this is the order it will be removed. And you can see that it is not kept in a sorted manner. So either we should arrange in such a way that every time an element comes, it should be arranged based on the sorted order of the priority. Otherwise, the front pointer will have to first move here, then it will have to move here, then it has to move here, then it has to move here. And there's a lot of wastage of space also. So you're actually finding some efficient ways where you are able to keep these elements in an ordered pattern so that easy removal is also done. So in some of the cases, maybe they just look at the min and max elements, that's all. So depending on the value of the element, you can decide the priority. So in a min priority queue, say you have elements like this. So a min priority queue will always go and find the element with the minimum priority. So either they look at the priority value or they look at the value of the element. What is the value of the element here? 1. That is the most minimum. So this will be removed first. Then this will be removed. Then this and then this. Similarly, max priority. So depending on how you have implemented the priority queue, you can remove the values from the queue based on the priority only. That is a specialty of a priority queue. Okay. In some cases, there are you can have elements which have same priority, but algorithms like that may not properly work. You can see. Okay, so you need to have to ensure a proper algorithm. You need to have a different priority, and we know priority queue is a very common scenario in our daily lives. Also, can you think of some examples where priority queue concepts are implemented? Of course, in our operating system, when you have time scheduling, around robin kind of scheduling algorithms, you may have give prior to there are queues where when an important what to say task is waiting, and if it has a very high priority, all the other tasks that all the processes that uh, OS is currently executing will be paused, and that task will be executed first. The important priority one will be executed, and then only the remaining ones will be executed. So there are cases like that. Other than that, also when you go to hospitals, maybe if you have paid a extra for a ticket or a to say for staying in the queue, you will be given more priority than other patients who are waiting maybe. So something like that. So basically, priority queues are implemented using heaps. So our concept is also what you have to learn in this module is basically two types of heaps. So we need to know what is a heap. So heap is implemented using a binary tree. Well, if you know what is a binary tree, right? A tree which has a maximum of two children. Okay. Why it's called binary? Because the maximum it can have is two children. So you can say simply it can be having a root or it can have a parent and one child, either like this or like this, or it can have two children, or it can be a leaf node also like this. So you can say it's a complete binary tree. This is basically a binary tree. What I've drawn here is a binary tree. So what is a complete binary tree? A complete binary tree is when you have scenario where a tree is filled maximum to the left side as far as possible without having any space in between. So such trees are known as complete binary tree. So as an example, I can show you first you fill this node, then you fill its left child. So this way, when a new node is inserted, this way you keep on filling the parent, the left, the right, then the next parent's left, and then it's right, then the next parent, whichever it is, it's left and right, and so on. There is not a possibility that you can leave a space here. You can leave a space here and then fill the fifth one here. That is not possible. So leaving a space here will not make it a complete binary tree. A complete binary tree should go in this manner. See, in this manner, like this. It should be complete in every sense. The only difference is, say, you can say I'm completing this. Now after 7, I can put on the 8 value here. This is also a complete binary tree because all the levels are filled. You can see every level of the tree is filled except for maybe the last level. This is the last level, which is filled max as far as possible to the left. If it is filled as far as possible to the left, then you can say it's a complete binary. If I draw one more node here, then that is also a complete binary. If I draw one more here, that is also a complete binary. Why? Because നമ്മൾ ലെഫ്റ്റ് സൈഡിൽ നോക്കിക്കഴിഞ്ഞാൽ you can see ഇവിടെ ഉണ്ട് 8, 9, 10 all of them on the left. അതെല്ലാം നമ്മൾ fill ആക്കി വെക്കുവാണെങ്കിൽ then towards the right നമുക്ക് പറയാം it's a complete binary tree. Okay. So that is a complete binary tree using a tree representation. The same thing is maybe this is the visual representation of this, but the same thing you can build using an array. Maybe the internal storage is based on an array. Say the root node will be placed at the first location. Then the second position will be for the left child of the root node. Third position will be for the right child of the root node. Then the fourth position will be the left child of the second node. Then you have a space for the second right child of the second node, say like this. Then you'll have a space for the third child's left child and then the right child of the third child and so on. So this way we'll be arranging in a sequence. So you can see there should not be any space in between. It should be complete. The beginning of the array should be complete. Only the end of the array should be empty if needed. Okay. So the last level only can be empty, but not in between. Maximum to the left, we should fill up all the cells of the array and go forward like this. Now this is an example of a max tree. So simply if you say a max tree, it may not be a binary tree. It can have more than two children. The simple tree means you can have n childs, okay, depending on the order of the tree. So max tree is a tree in which the value of each node is greater than or equal to those of its children. So we'll see what it is, and it may not be a binary tree. So you can see this is an example of a max tree. What is the specialty here? I was talking of generally what is a binary tree. When we talked about what is a complete binary tree, we didn't discuss what is a heap, right? So we are coming to that. So we can see this definition of a max tree, which shows that when you take any node, say for example the parent node 9, now this is also the root node. The root node 9, you can see the values below the root node are 4, 9, and 8. So they can have equal priority, I said like before, right? So here 9 and 9 are equal priority, but 9 is greater than 8 and 9 is also greater than 4. You can see every parent node will have a value greater or equal to its children. So that is how this is. You can see here 9 is greater, 9 is equal, and 9 is greater. So now let us take this parent set of node. Then you can see this one is equal to its child and this one is greater than its child. This is a leaf node, no more children. You take 8, you can see that 8 is greater than 7. You take 7 as the parent, then you can see 7 is greater than 3, 7 is greater than 1. So if you have an arrangement like this where the children are less or equal than its parent and the root node contains the node which has a maximum value among all of them or maybe equal. Okay, so that is known as a max tree. Similarly, what is a min tree? The opposite of that. When you take any set of parent node, its children nodes will be, the value of the children node will be greater than this one. So you can see this will be less. 2 is less than 4. 2 is less than 9. 2 is less than 3. 4 is equal to 4. 4 less than 8. 3 less than 7. 7 less than 9 and 7 less than 9 again. So it does not matter whether the left side is lesser or the right side is less, greater as in a binary search tree. Here we just check whether the parent node is greater than or equal to its children or the parent node is lesser than or equal to its children in case of a max tree and a min tree. So the same concept is when you talk of a tree means it will have more than two children. So you can see how many children are there. 2 has 3 children, 3 has only 1, whereas 7 has 2 and so on. But when it comes to heap, it is a binary tree. That is the only difference. What is a binary tree? Maximum it can have is only two children, and it should be complete in every nature. You can see this is not a complete tree. Why? Because you fill here and then 9 does not have any child and you move on to 3 and you fill the nodes for tree. It's not a complete because tree cannot be complete. But when it comes to a binary tree, you can have a complete binary tree like this. So what is a max heap or a min heap? It is basically a max tree or a min tree that is also a complete binary tree. So the definition is basically it is a complete binary tree where every parent will have a value. If it's a max heap, how do you define it? Max heap is a complete binary tree where every parent will have a value that is greater than equal to of its children. Got it? That is known as a max tree. Now, when you define a min tree, it will be a complete binary tree where a parent will have a value lesser than equal to that of its children. And when we arrange the tree in this way, the root node in a max tree will be the most highest or the maximum value from all the members of the tree. And similarly, when it comes to min tree, the root node will have the least value. Okay, now let us look at this example. So is this a max tree? We have 14 here, 12 and 7, that is fine. 12 here, then 10 and 8, 7 and so this is a proper max heap. What about this one? You have a 9 here, a 6 here, and all of them are reducing, right? But is this a complete binary tree? No. Because why? We did not fill the right child of 9 and instead we went down one level down beyond 6. So that is why it's look the property of this looks like a heap tree, but it's actually not a heap tree. Why? Because it is not a complete tree. Okay, complete binary tree. Whereas this one, is this a max heap? Yes, 30 is greater than 25, so it's a max heap, but and it is also a complete binary tree. In this case, this is also a max heap and also a complete binary tree. Okay, so this is the definition. What is a max heap? The key present in the root node must be the greatest among all of the children, and this property is recursively followed for all the subtrees. So you define it on the basis of the root node. You say that the root node is the greatest among all of these children. Look at all the children of the root node, it is greatest. And this property must be available for the all the subtree. If this is a subtree, left subtree and right subtree of the root node, this also follows the same property. That is, it will have a greater value than its children. When this is a subtree, it will have a property that it follows a greater value than its children, so on. So this way you can say the same property recursively follows all the subtrees below. So that is the definition of a max heap and a min heap. Min heap minimum among all the elements. That's all. And the same property moves forward. Or you can also define it like I said before. It's a complete binary tree where the parent node should have a value greater than or equal to its children or lesser than equal to children for a min heap. Okay, so I hope this is clear. Now we'll see how this tree is created basically. Initially, when you get a set of values, how do you create a max heap? That is one thing. So you have to actually initialize the tree in the beginning, and then only you have to insert new values or delete a value and so on. Okay, this heap tree is also related to heap sort. So if you have learned the heap sorting algorithm in data structures, you can see that the way the heap tree is arranged, and then you remove a value from the heap tree repeatedly, eventually you will be sorting the element. Why? Because the topmost element of a heap tree, that is a root node, will always contain either the maximum value from all the members in the tree, or it will also contain a minimum value. So you just have to remove the root node every time constantly and rearrange the heap so that you get a sorted set of array. Okay. Now, what is a max heap? So this is a example of a max heap. It's a complete binary tree. Yeah, because we have elements in the first location. See here, first, second, third, fourth, fifth, sixth, seventh, eighth, ninth. Even though the right side is not filled, but it is complete towards the left. So you can say it's a complete binary tree. This is also a max tree. This is a min tree, the same concept. Okay. Now this is array representation. Some of the textbooks they may use the array's zeroth index also, but in some textbooks they may not. It depends. Both are correct. Okay, you can start from here also. So this is the basic idea. So 9 is the root node, then the left child of the root node and the right child of the root node will be here. And this one's left and this one's right will be here. Then this node's left and this node's right will be here, and so on. Then once you're over with these three, then this one's left, 6 in the left, 5, 6 in the right, 1, and so on. We keep on doing this. So you can see all the cells in the array are complete in every sequence when you move from right to left. And there is an equation for finding out when you're implementing this, there's an equation for finding out how can you find out the left child and right child. You can have a revision, okay, for that. Now, what are the different operations you can see here? Basically, it is a complete binary tree. So a complete binary tree is basically having a height of, you can say, log. Basically, it's a binary tree. So you have the log to the base 2, binary log, you say, and then of n, where n is the number of elements in the tree. So insertion will be big O of log n to the base 2. Deletion also will be log n to the base 2. But initialization means what you're given, say, some 50 elements or 10 elements, whatever it is. The first time you have to create the tree. So it depends on all the elements given to you. Otherwise, but when it comes to initial insertion and deletion, you may have to look at one half of the array, not the whole. We don't have to check with all the elements. We have to check only maybe few of the elements. That's why it comes to a reduced value, that is log n to the base 2. But when it comes to initialization, all the 10 elements will be have to be accessed, so that you have to create a tree for the first time. Okay. So we'll see how to insert into an element into a max heap. We'll take an example of a max heap and see how a new element can be inserted. Say for example, this is a given tree, 8, 9, 7, 6, 7, 2, 6, 5, 1. These are it's already arranged in a max heap. Now, given a max heap, our question is you're given a new element 5 and you have to insert it. So being a complete binary, the next apt position where it has to be inserted is after 1, that is 5. So suppose that this was your array in implementation. 9 is here, 8, 7, 6, 7, 2, 6, 5, and 1. You can see which is the last location in the array, which is the last location in the array, 1, right? So which is the next position for inserting a new element. That is the next location after 1, that is 5. And when you look at it visually, it is over here. Got it? So we have to insert it to the left of 7. Now once you insert it to the left of 7, we have to check whether it violates the max heap condition. Does it violate the max heap condition? We have to see whether the element that is greater, whether the element acting as a parent of 5 is greater than 5. Then only it becomes a max heap, right? Because ഓൾറെഡി സെറ്റ് ചെയ്തിരിക്കുന്ന ഒരു എറേ അല്ലെ ഒരു ഹീപ്പാണ്. അതിനകത്തോട്ട് ഒരു പുതിയ എലിമെന്റ് വരുമ്പം മാക്സ് ഹീപ്പിന്റെ കണ്ടീഷൻ അത് വയലേറ്റ് ചെയ്യും. So we have to find out where it has violated. Is there any problem? No, there is no problem. That is, everything is fine because it's not affecting any of the parent or its sibling. So we can say that this is done. Now, suppose I give you another element, say 20 to be inserted. Now you can see naturally 20 is a greater element than 7. So when you insert 20 to this left side, but you cannot say it is not, 7 is not greater than 20, right? So we have to do something so that it becomes a heap again. It's not a max heap now. So what is the first natural thing that we can do is you swap these two values, because we cannot go to the left of the tree or the right of the tree. It's because it is below 7. So the first thing that comes to our instinct is we have to swap the values 20 and 7. Now when 7 was here, 8 and 7 did not have a problem because 8 was greater than 7, right? But when 7 moved down a position downwards, like 7 moved to a position downwards in the tree, and 20 is coming as a new node here. So naturally it will affect the nodes that are above 20. So what you have to find out, you have to see whether uh, 20 and 8 has a problem. Yes, 20 is greater than 8. We need the parent to be greater, right? So again, swap. Now, because 20 is coming in position of 8, is there a problem? Yes, it will affect the parent of 8, previous parent of 8. So what was the parent of 8? It was initially 9. Now when 20 comes here, it cannot be placed there. So find the correct position of 20. And we found out that because 20 was the largest element in the array or in the heap, naturally it found its way to the top of the tree. So now it has become the new root node. Okay, you can see that. Now, so this way you can see every time we insert a new element, so where this is the position where the element has to be inserted. We swapped 20 from here till here till here so that it found its correct location in the heap. Now, is this a heap tree? Yes, because 20 is greater than 9 and 7, 9 is greater than 6 and 8, 7 is greater than 2 and 6, and so on. We have not affected this part of the tree or this part of the tree. The only path it followed was like this. Got it? So this way we have to, so that is why the insertion takes only O log n to the base 2. It does not affect the entire set of nodes. It only affects a path of the tree, or you can say it only affects the height of the tree. What is the height of a tree of a complete binary tree is basically O log n2. That is why the complexity is also big O of log n to the base 2. Okay. That is what is written here. At each level, we'll be doing the theta 1 work, but the height of the tree is log into the base 2. So whenever we move upward, we are moving maybe maximum till the root node. So from the leaf node, we are moving till the root node. Similarly, let us look at deletion from a max heap. Deletion from a max heap, say, can be done like this. So suppose you want to delete the element, say 20. We just remove it from the tree, and we cannot just disrupt this tree by removing this node. That is not possible. So what we do here is we take, you can see delete 20 like this, but we keep the tree intact. Tree വലിയ മാറ്റങ്ങളൊന്നും വരുത്താതെ അതുപോലെ തന്നെ വെച്ചോണ്ട് deleting a node should have a reduction in the number of nodes, right? So the easiest way of deleting an element is deleting the last location. Suppose you had the array like this, so 20, 20, 15, 7, etc., etc. And the last node was 8, right? So when you delete 20, what is the normal procedure in an array? This space becomes vacant, so you have to shift all the elements, right? So that is not an easy way. So what can be done without affecting all the elements in between? The most easiest way is go to the last element and bring it to the beginning. Go to the last element, remove it from the array. So when you remove it from the array, this link will be gone, or this, it will not affect the remaining of the elements, and just bring it to the first location. But when you bring it to the first location, what happens? The max heap property will be disrupted, right? Max heap and a property 30 what you have to do now? 8 in the correct location. So find out the correct location of 8 and bring it downwards. So basically, these two algorithms, you can see in insertion, what happened was 20 was moved forward, upward, 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 and it went to the top. So this is basically known as, you call it as bubbling up algorithm, because insertion, you start from the bottom of the tree and you move towards maybe maximum to the root of the tree. But when it comes to deletion, usually what happens is you bring a smaller element to the top of the tree and you bring it down to its correct location, maybe till the leaf node. Maybe you have to move to the last node. Okay, maybe somewhere 8 will find its place in this level, or it will find a place in this level. We don't know. So we have to compare it with its children and bring it down. Okay, so now what is the next step? The next step is to find 8's correct location. So this is known as bubbling down. That is what I meant. So bubbling up for insertion and bubbling down for deletion in the max heap. We compare 8 with its two of its, because 8 is the root node. It will have actually maybe two children because it's a complete binary tree. So among both of its children, the smaller one cannot be exchanged upwards, right? So you have to find out which one is greater, 15 or 7. Since 15 is greater, we'll be only swapping 8 with 15. See, like this. Now, is 8 in the correct position? We have to check with its children. Its children are 6 and 9. You can see 9 is greater than 8. So it's not a max heap property. 8 is not in the correct position. So we need to exchange 8 and 9. Got it? Now check with its children again. 8 has only one child, 7. 7 is lesser than 8, so 8 is at the correct position. Oh, so this way, now what happens finally? This is again now a max heap. And the next, in the previous step, you can see after 20, which was the next highest node in this, the highest value in this was 15, right? So once 20 is deleted, who should come at the top? 15. You can see naturally 15 came. So this way you can find out this is how heap sort works. You remove 20, then you remove 15, then you'll be removing 9, then you'll be removing 8 and so on. So this way you can find out in descending order of if you're deleting from a max heap, you can find the elements in a descending order. This way you can remove every element. So deletion from a max heap cannot take place elsewhere. You cannot delete any other element. You can only always delete the root node. And one solution is of deleting the root node is cut off the last node and bring it to the beginning position so that the root node is only the value of the root node is deleted, but the root node stays there and you insert another value there, then bring it down to the correct position. So this way also, what was the complexity? There's a possibility that 8 could have found its location in the last level. So from the root node, you can move to the last level. So what is the height of the tree? Log n to the base 2. So the complexity is O of log n to the base 2. Now, next question is, suppose I'm giving you 10 or 12 elements directly, and I'm asking you to initialize as a max heap. So now currently it is not in a max heap order. I'm giving you some elements 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, how do you initialize it? The first step is we arrange it in the form of a complete binary tree. Whichever value it is, whatever value, we just put it in a complete binary tree. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Now what we have to do is we have to start from the bottom of almost half of the tree. So you can see we start from the n minus, the n by 2 item. So if you have total 10 or 11 items, almost maybe the fifth or sixth item will be the element to be arranged from. So start from the rightmost array position that has the index n by 2. Okay. Now what happens is we find whether this subtree is following a max heap property. If it is not following, we arrange it, then we move forward and so on. So you can see you're basically at the last subtree. This is the first root and its child. Then this is the second level of root and its child. This is the third level of root parent and its children. Then this is the fourth level. This is the fifth. You can see you reach the last level, right? In the last level, we not check 10 and 11. We arrange 5, then we arrange 4, then we arrange 6, 3, sorry, 3, and so on. So this way we'll be arranging all the elements. Okay, so we'll start from 5. Now, how can you make 5 as a correct max heap position? Just check with 10 and 11. Whichever is greater, we swap it. So we know 11 is greater, so we swap 11 and 5. Now you can see that move to the next lower array position, which is the next lower array. We will not move forward. We know that's still not a max heap, but still we wait. We move to the next location because earlier we were in this position, in this position, we arrange this subtree for the time being. Now we move to the next position, that is 4. We were at n by 2. Now we move to n by 2 minus 1 the location. Okay. So now what happens? Arrange this. Is it in a correct max heap? No. So what we can do? Compare 8 and 9. Whichever is greater, we swap those. Okay. Now we move to n by 2 minus 2. So this position is over. This is over. Now we come here. Now what you have to do? 3, 6, and 7. 7 is greater, so exchange with 7. Now we move to the next position, that is 2. Now but the reason why even though 11 was at the wrong position, we did not go up is because we could not check this side, right? Because we did not check this side, we need to see how this has been that is, even though they were at the wrong position at these two levels, when you come and arrange this one, automatically the greatest of the two will come forward. So there was no need of changing it in between. So because we are moving at the parent nodes every time. Now check 9 and 11. So we have the greater one, that is 11. And then we swap these two. Okay. So move forward, swap these two. And you can see that when we swap these two, 11 comes here and 2 has to be placed here. But this was already a maxi. And now we are bringing a new element 2 downwards. Okay, so now we should find a home for 2. So how do you find a home for 2? Just compare it with 10 and 5 and see which one is the greater one and just move it forward. And then are we able to place the new element there? Yes, so we can do. Now we again move forward to the next parent kind of location, that is 1, and we compare 11 and 7, that is children. 11 is greater, so we move forward. Now when we place, this was already a max heap, right? This position was already a max heap when 11 was there. Now when we shifted 11 here, a new element is going to come here. That is, ഒരു മാക്സ് ഹീപ്പ് ആയിട്ട് ഇരുന്ന സ്ഥലത്ത് പുതിയൊരു എലിമെന്റ് വരുമ്പോൾ നമ്മൾ ഡിസ്റപ്റ്റ് ചെയ്യും. അപ്പൊ പിന്നെ നമ്മൾ അതിനെ ഒന്ന് ടെമ്പററി പൊസിഷനിൽ വെയിറ്റ് ചെയ്തിട്ട് you have to find out where to place it. So this 10 has to be placed here and 1 has to go down. Now can 1 be placed here? No, still no. Why? Because 2 and 5 are greater. So I find the greatest and exchange that, and now 1 can be placed here. Got it? So this way we find out the different way of initialize. So you can see we were given random set of elements, and after going to the half location of the index of the array, we found out without affecting subtrees, you find out which is the element that can be swapped every time. So now what happens here, even though you started at the half of the array, you touched almost all the elements, because when you had to move 1, you have to go down the tree multiple times. You may have to go up the tree multiple times. So basically the complexity of this is big O of n. So initializing a tree is affected by all the set of elements in the array that are given. So you can say that n is the maximum complexity of the array. So this is basically an introduction to heaps. Now we'll move on to the main topic of our module in the next lecture. Thank you.